Good morning. We have a lot to cover today, so I will start. Today will be another example so that you understand how to do the balance, and eventually we will find the velocity profile just like in the last example. Last example is basically flow in rectangular coordinate. For today, we will try to shift into different coordinate. This one is the cylindrical coordinate. Okay, the example is basically a flow in a pipe, in a circular pipe, and water is going down according to gravity. Okay, and in similar manner, the steps for doing the problems start with coordinate. And we choose the coordinate according to the look of your system. If it looks cylindrical, we pick cylindrical coordinate. Okay? Then we have to assign the origin point. As I said, one axis supposed to be going in the direction of the flow. That would be easier. Okay? So if flow is going down, the axis in cylindrical coordinate that will go down supposed to be z-axis. Okay? In cylindrical coordinate, there are three axes. R, that means from my center going out, this is R direction. So it can go this way, that way. It will be the same as long as you go from the center outward. That's R direction. Okay? Theta, you go around. So anything go this way, that means it has velocity in theta component. And then Z going up and down. Okay? So in this case, Z axis is supposed to go along with the flow. So I will have my z-axis going down and located at the center of the pipe. Okay? Now let me ask you this. If z is going down along with the flow, r, would r be from origin to the right or to the left? If you try to answer my question by looking at your right hand, that means you are not understanding cylindrical coordinate. Unlike rectangular coordinate, x, y, and z follow your right hand, right? Cylindrical coordinate does not. In cylindrical coordinate, r goes from the center. So that means this is r. This is also R. Anything going outward is R direction. Okay? What about theta? Theta is something going this direction. That's theta. Okay? So we set up the axis already. Next steps, identification of velocity component. We will have three components of velocity. The velocity as a vector can be expanded into VR, v theta, vz. This is important question. Which one is zero? Now, we know for sure Vz is not zero. That's easy. So I will answer this for you. The hard part is yours. Is VR zero? Is V theta zero? Now think about this. If V theta is not zero, what would the flow look like? It has to go around in theta direction. So if that is V theta, the fluid must go like this, right? What about if the fluid goes like this? Just like when you go to the bathroom in the morning, it goes like this, right? In that case, there are V theta as well as Vz, right? So in that kind of flow, there are two components. If it goes like this all the time, does not go down, it means it has V theta only. If it goes down alone, it's supposed to have Vc only. Okay? What about Vr? In this picture, V theta would be 0, right? What about Vr? If there is Vr, what does it look like? Cylindrical coordinate with Vr. Vr means the fluid must go in R direction. If you have flow in this direction, there is Vr. Can you imagine something with Vr in cylindrical coordinate? You learn in unit operation 1, stir tank, right? And in unit operation 1, you learn how to pick the blade. Did you? There are several types of blade. There are turbine blade, four blade turbine. There are rotor blades. Different blades give you different velocity distribution. For instance, some blades, if you have flat blades, it goes this way, right? If you have propeller or propelling blade, it goes outward. Once it hits the wall, it goes down. Like this. Okay? And circulate back to the center. That's a mixing tank. In this picture, do we have Vr? This is going from the center outside, right? Outward. So this is Vr. So you have Vr in this part. Do we have V theta? In this picture, do we have V theta? It's a mixing tank, it's go around. So there is V theta. Is there any Vz? Yes, there is Vc over here. It's go down and going up, right? The word up like this, that's Vz. So in this picture, you have all three components. All right? Now let's try something else. I said this is very important, so let's practice a bit. Suppose I have a pipe, okay? Circular pipe. Now, if in the middle I have some obstacle, for instance, I have circular blade installed in the middle of the pipe. Water is going down. Of course, there's Vc, there's Vz. Now, if this is the system of my interest, is there any V theta? Is there any swirling of fluid? You have to imagine that fluid goes down and then hits the plate, going around the plate like so. This seems to be the streamline of velocity, right? Is there any v theta? No. In this picture, there is no v theta, no swirling. Is there any VR? In this case, this part, velocity is going out. That's VR. Okay? Understand? What about if I have circular pipe? Okay? Liquid is flowing down. But now, there is a fin going down. The fin here installed, if it is rotating tank or if it is stir tank, this is called baffle, right? But if this is just a pipe and you flow this down, this is just a fin. Is there any VR? So you have to imagine the streamline of the flow. It goes down. Is there any swirling? Is there any going from the center outside? Now in this case, you have to see that there is no VR. There is no v theta. Only vz. Can you see that? Okay? So in this case, VR is 0, v theta is 0, vz is not 0. So once you set this up, next question is asking yourself, vz is not 0, it is function of what? R theta z. Is vz changing with respect to r? So use your finger, starting from origin point, going in r direction, and imagine your fingers, does it experience different flow? Or in r direction, can you find 2 points which have different velocity? Can you? In r direction, at least there are 2 points with different velocity. At the wall, velocity is 0 under no slip condition. Outside the wall, is not 0. So right now, vz is changing with respect to r, right? So it is function of r. Okay? So in this picture, if you go in r direction, velocity at the center is high. The velocity at the wall is 0. Right in between, there's supposed to be some kind of gradient of velocity. This is vz as a function of r. Can you see? Velocity is going down. This is vz. But magnitude is changing with respect to r. So vz is function of r. What about theta? Is vz a function of theta? Now you have to imagine theta is going in this direction. So going around, is there any change in velocity going down? So from this point, going around it, clockwise or anti-clockwise, do you think velocity change? No. So it does not change. It's not function of theta. This kind of picture does not happen. What about z? Is vz function of z? So imagine, does it go from small velocity going faster and faster. This kind of thing means velocity changing with respect to z. Do we have one? Again, just like last examples, if you consider short length of the pipe short enough to ignore acceleration, then you can approximate that Vz is not zero. I'm sorry, Vz is not function of z. Okay? So in this case, you ignore acceleration. Understand? Now, let us consider this one. This one, we know that Vr is 0, V theta is 0, Vz is not 0. So let's try this as an exercise. Flow in this pipe with the fin, is Vz function of R? You go in R direction, can you find 2 points with different velocity? Yes. Center has some certain velocity. At the wall, velocity is 0, right? So it is function of R. In this picture, is Vz function of theta? You go around in theta direction. Does Vz change when you go around? Can you see that it does? Because here, let's say you go start from here, going around it under same radius. Here velocity is not 0, right? But once you hit this wall, velocity is 0 at the wall. So you go around z direction, at least these 2 points are different in terms of velocity. So it is function of theta. Okay? Is it function of z? No, it is not function of z, because same thing, when you ignore acceleration, all velocity is uniform. Okay? What about this picture? Now we set it up. Vr is not 0. Vz is not 0. V theta is 0, right? This picture. Is Vr a function of R? In this picture, is Vr a function of R? That means velocity in R component, this is R component, right? Does it change with respect to radius? Does it change with respect to radius? Yes, it is. Okay? Does it change with respect to theta? So this component going from the center outward, does it change when you look at different angle? No, this one does not. Does it change with respect to z? You should see that it is function of z. Why? Look at this. At this point and at this point, different z. This point, you don't have velocity in R component. In other words, Vr is 0 here. At this point, you start having Vr. Vr is not 0 here. So VR is changing with respect to z. Can you see that? So in this one, it is function of z. What about Vz? Is it function of r? So for Vz, now we go down. This is Vz. Does it change with respect to r? You go in r direction, can you find 2 points with different Vz? At the wall, it's 0. Outside, it's not. So it's changing with respect to r. It is function of r. Is it function of zeta? So you consider downward component. Does it change when you go around it? No, it is not. Does it change when you go down? This component and the component velocity is going down here. It has to be expanded to 2 directions, right? This component here and this component over there might not be the same. They're not the same. So it is function of z. Okay? Understand? One last example. Now imagine a pipe, circular pipe, empty pipe. Put water down, but now if you allow acceleration, what would happen? If you allow acceleration, Vc is now function of z, right? What else happened? I told you last time from very beginning of last example that suppose you have water stream going down. Once it has acceleration, velocity component, Vc here and Vc there, are not the same according to acceleration. But in order to keep the stream continuous, there's no way to keep cross-section area to be constant, right? So it must somehow taper down. The shape looks something like this. So you have flow going down and going faster at downstream. Now this kind of flow, is VR 0? Is V zeta 0? Is Vz 0? Which one is 0? I can answer for you that this one is not 0. Sure, of course. What about VR? Is it 0? Can you see that the way it's tapered down like this, it requires velocity component this way. In other words, if you try to put velocity vector over here, you can see it goes down together with the surface. And this line is not vertical. You have to expand into Vz and Vr. So there is Vr. Okay? Is there any V theta? Is there any swirling? Not at this time. Okay? So you see that the assumption that acceleration is neglect. This assumption, you ignore acceleration, not only it affects this part, it also affects this part. Okay? So if you have to include acceleration in the calculation, you have to somehow include VR not equal to 0 as well. Okay? Any question regarding this? All right, as I said, this step is critical. It is extremely important. You have to correctly identify velocity component which is not zero and correctly identify whether it is function of what. All right? Because this function will define the shape of your shell. I told you that when you analyze velocity components and you found that Vz is a function of r only, that means shell in r side will be thin. So shell, if you consider shape of the shell in r, is supposed to have thickness of delta r, or thin in r direction. It is not function of theta, so your shell should cover the whole length from 0 to 360 degrees, right? So theta should cover from 0 to 2 pi radian. Z, it is not function of z, so therefore your shell must cover the whole length in z direction. It should cover from 0 to L. According to all these red letters, what does the shell look like? It must cover 2 pi. So it must be cylindrical, right? It must cover the whole length of L. So it's go down from top to bottom. But it is thin in R direction. So it looks like this. This will be your shell. Okay? If I cut it in half, you see that the shell looks like this. This is half of the shell. Okay? Now, since we have Vz only, that means we now have z momentum only. For z momentum, we will consider 3 of the fluxes: Rz, theta z, zz. As I said, the second subscript dictates direction of the momentum. So if we have z momentum, we consider all fluxes with the second subscript to be z. All right? And we know that phi Rz is tau Rz plus rho Vr Vz. Theta z would be the same. For Zz, you just add one more term, which is pressure. Okay? And now since we already identified that Vr is 0, this term will be 0. Vz is 0. Vz is not 0, so you have to keep this term. At least this term is not 0. All right? Then, according to Newton's laws, tau Rz is minus mu dVz by dr plus dVr by dz. Tau zeta z Now you should notice that in cylindrical coordinate, it's not exactly the same as in rectangular coordinate. Now you see 1 over r over here. That follows cylindrical coordinate. All right? All the equations will be given in examination anyway, so you don't have to worry about remembering. And they are in the appendix of your textbook. Okay? Now, next step is eliminate all terms that are 0. For instance, VR is 0. This term will be gone. V zeta is 0. This term will be gone. What else? Now we know that Vz is a function of z. So therefore, this term is not 0. Anything highlighted in blue must be kept. Anything highlighted in red will be gone. Okay? What about this term? Is it 0? Is Vz function of zeta? No. So the whole term here is 0. Please notice, this one, VR itself is 0, so I highlight only VR. This one, the whole term is 0. Okay? What about this term? Vz is not function of z. So it is not function of zeta. I'm sorry, it's not function of z. When you partially differentiate it with respect to z, it's 0. Okay? And again, I said, whenever you work with liquid, you can assume it to be incompressible fluid. For incompressible fluid, this term will be 0. Okay, we will confirm this in chapter 3. So that means tau z is 0. Tau zeta z is 0. Zz is 0. This term will be gone. Zeta z will be gone. So we have only tau rz left. And this term, is pressure 0? It's not 0, isn't it? So pressure must be kept as well. Okay? Any question? All right, couple minutes. Write it down just to make sure that you get the idea. All right, so that means phi theta z is 0. This one is 0. Phi rz is not 0. And phi zz is not 0. So from all three fluxes, we will consider only 2. Okay? Let's start with RZ. Phi RZ is supposed to go according to Z momentum and transferring in R direction. So the direction of the transfer should go this way, going in and going out. This would be phi RZ. And as I said from the very beginning, R direction goes from center outward. So this is also phi RZ. As long as it goes from the center outward, doesn't matter whether it's go left or right. Both of them are considered RZ. Okay? As I said, double arrows means the direction of the transfer. We know that the first direction, according to momentum, it goes down. Okay? I'm not going to write it down, otherwise it will be confusing. For ZZ, it is transferring in Z direction, so it goes like this. In and out. This would be ZZ, going in and out. Okay? So, ZZ going in takes place at Z equal to 0, going out at Z equal to L. RZ going in, this is RZ, going in taking place at location R, generic location R, going out at R plus delta R. So now we define fluxes, we are ready to put it in the balance. Let me write this down. So this would equal to minus mu dVz by dr. Please note that I changed from partial differentiation to total differentiation because Vz is a function of R only. It's not function of other variables. So I can change partial differentiation to total differentiation right away. It will be easier. Okay? Now, I'm going to show you the balance for each surface. Let's start with top and bottom surface. That means this surface going in and going out down here. Okay? So the flux associated with that direction must be ZZ. Okay? So the momentum going in, that's supposed to be flux multiplied by the area perpendicular to the transfer direction. What is the area? Highlight here. How would you calculate the area? You can do it two ways. First, you can say it is pi r plus delta r square subtracted by pi r square, right? That's one way. Or if I said that the thickness of this delta r, the thickness here is delta r. If delta r is really, really small, just like when you have a piece of paper, fold out like this is your shell, okay? if I cut open, the height here is L. The length here is 2 pi r, right? In that case, I can say that it is 2 pi r times the thickness delta r. This one is approximate. This one is exact. Which one is easier? Think about this. Last example, we have to put this in the balance, somehow convert this into differentiation according to the definition of differentiation. This kind of thing, square, would give you hell. So instead, using this one would be much, much easier. This will be true as long as delta r is really, really small. Okay? So we will prefer this one. This one will be a mess. Okay? So in taking place as z equal to 0, out would be the same, except it takes place as z equal to L times 2 pi r delta r. That's top and bottom balance. Then you have side balance, sideway. Sideway means you consider this area around the shell going inward. So the flux associated with this area would be RC. Okay? So N would be the flux itself, RZ, multiplied by the area. The area of the inner surface should be 2 pi r times L, right? Circumference of the inner circle times height. So that would be 2 pi r times L. It takes place as generic R. For out, it will be RZ at R plus delta R. But now the surface should be the surface of the outer circumference. And outer circumference should have the length of 2 pi r plus delta r. This would be 2 pi r plus delta r. This would be circumference of outer circle times L. Okay? Now the tricky part is, in this case, I can say that it is 2 pi L. Taking L out, taking phi and r together, I get r phi rz. Can I do that? Of course I can. And then I can say that the whole thing takes place at r. Can I do that? This means the first variable takes place at r. The second variable is taking place at r as well. Okay? So if you put r in here and r over there, you get r and flux at r. Okay? So same thing for the output. I can write 2 pi L, and then this is location and the flux at that location. So I can also say that it is R flux at this location. So think carefully about this one. I will say R at this location and flux at this same location. So basically, I put R plus delta R to replace this variable and put the location here. So I can do that as well. Do you understand? Okay? This is important because otherwise you cannot deal with this term when you put into the balance. All right. I'm running out of space. So let's erase this first. Okay? So for the balance, you take in minus out. So I'm going to take this pair together first. In minus out. That will give you 2 pi r delta r, that's the area, times the flux. Flux, phi here, zz, is equal to rho vc squared plus pressure from what we discovered earlier. Okay? So I'm going to take rho vv together. That would be rho vc squared as z equal to 0 minus rho vc squared as z equal to L. The first term plus pressure as z equal to 0 subtracted by pressure as z equal to L. The second term. That's the flux in and out from top and bottom. Then in and out from sideways. So I add 2 pi L. This flux is basically tau Rz from what we found. So I can say it is, so basically this term would be tau Rz. All right? So it is R tau Rz at R minus R tau Rz at R plus delta R. That's in and out. The third term must be a force. Okay? And force should be associated with gravity. Gravity, force by gravity, is basically mg. So my force now would should equal to mg, and mass is basically density times volume. Volume must be volume of the shell because we are balancing around the shell. Volume of the shell, you can use the area, which is highlighted here. This is top area. If you multiply by the length, you get volume of the shell, right? So the volume would be 2 pi r delta r times L. That would be volume times G. Understand? All right. So I'm going to put force down here. Rho times 2 pi r delta r L G equal to 0. That's equation of balance. Now you can see that if we use this kind of term, this would be complicated, right? If we use what I erased here, the way we calculate the highlight area here, this term will be complicated. But if you simplify it at first, then you can work on this equation. Okay? Now, if I cancel 2 pi here, 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 2 pi will be out. Next step is try to determine which pair cancel out. Is this pair canceling each other? Are they equal? Density will be constant. Velocity Vz, this is Vz at one position and Vz at another position. Now we know that Vz is not function of z. So changing z does not change velocity. So this term canceling each other. Okay? What about pressure? In our last example, or previous examples, pressure, two pressure terms canceling each other. What about this term? Pressure at z equals to 0 is pressure up here. This is pressure at z equal to 0. Pressure at z equal to L is down here. Do you think pressure of these two levels will be the same? No, they're not. They're not the same. So this must be kept. All right? These two terms obviously cannot cancel each other because there is velocity inside. If you cancel it out, nothing left for calculation. Okay? So I'm going to rearrange the equation so that we can change into differentiation. All right, let's copy R delta R, PZ. Let me call the PZ as z equal to 0, in short to be P0, subtracted by PL. Okay? Then I will have this term plus R delta R oh, I have L over here, right? L rho G 0. Okay? So if I eliminate this L, I will have L as a denominator over here. And then you see that if I flip this, or bring these two terms to the other side of the equation, I will end up with R plus delta R first, subtracted by tau R Z times R at R, equal to, the other side would be pressure. If I divide the whole equation by delta R, I will have denominator here to be delta R. Delta R here will be canceled out. So there will be R over L plus R rho G. Okay? And this would follow definition of differentiation. So you see that unless you work on this, you cannot come up with this structure. And that will be a mess. So whenever you work with cylindrical coordinate, please remember bring R and tau together. Okay? So if you take limit delta R approaching 0, then this term turns to be differentiation of R tau Rz with respect to R. Right hand side remains the same. I am going to bring R out. So I have pressure 0 subtracted by pressure L over L plus rho G times R. Okay? Now on the right hand side, if I extend this division line to here, I need to multiply by L. Okay? Then, if I extend it further, I can subtract it by rho G times 0. Remains the same. This term is 0. I add this term intentionally so that I can combine this term and this term together. Okay? So if I define pressure at location I minus rho G times location itself, I call this one capital pressure, I. This is called modified pressure. Okay? So first, modified pressure is P0 and G as 0. That would give you modified pressure P0 and PL and rho GL. That would give you modified pressure at L. This would be negative. The whole thing divided by L times R. Okay? So by definition, modified pressure is basically absolute pressure combined with head space, the head of the liquid on top of it. The change in pressure here is still considered as pressure dropped. Same thing, it still has unit of pressure. So the difference here would be similar or almost the same as conventional pressure dropped. Okay? So if I integrate, I end up with R tau Rz. Oh, let me write down on the other side. If I integrate, you end up with R tau Rz equal to modified pressure 0, modified pressure L over L times R squared over 2 plus integration constant C1 after integration. In order to find C1, we need boundary condition. Okay? So as I said, boundary condition is supposed to be located somewhere in the system. Usually it will be appear at the boundary, But it is not always that. But somewhere in the system where you know the location and you also know the variable. In this equation, you want to know tau. And tau is difficult to find. Okay? Sometimes you need mathematical trick, just like this one. I will say that if I divide the whole equation by r, this r will be gone. Let's remove this r. Square here will be gone. And then I have r as a denominator here. Okay? And the trick that I said is, this equation is applicable everywhere in the system, including at the center. At the center, r is 0, right? So, at r equal to 0, if this term exists, equation is not solvable. But you know that this equation is applicable to the whole system, including at the center. So that means, mathematically, it means that if I set at r to 0, tau rz is not infinity. Okay, that means this side has to be some number at r equal to 0. How much? We do not know, but we know that it is not infinity. But if you allow this term to exist, it would end up with infinity. The only way that tau will not be infinity is that C1 is 0. So if C1 is 0, this term will be gone. The whole equation is true. So this is mathematical trick that I said. Okay? One more time. You need one more time. As I said, the whole equation is correct everywhere in the system, including at the center. But at the center, r equal to 0, that makes this term infinity. If it is infinity, it means that tau also infinity, which is not true. We know that tau must be definite, must be number. That is not infinity. The only way that makes tau not infinity at the center is that this term will be gone. If this term does not exist, the rest of the equation remains correct everywhere, right? So if I say that r equal to 0, tau is not infinity, makes C1 0. So if C1 is 0, this term will be gone. The whole equation, what we have left, is applicable everywhere. Okay? So that means tau Rz is equal to pressure of P0 PL over 2L R. This would be shear stress profile. Okay? And we defined earlier that tau Rz is minus mu dVz by dr. So if you move minus mu over here, and integrate equation should give you Vz. That would be minus pressure over 2 mu L. Integration of R gives you R squared over 2 plus another constant. In order to find this constant, we need another boundary condition. Okay? So boundary condition, in order to find that, you need to ask yourself, do you know velocity anywhere in the system? At the wall, right? At the wall, velocity is 0. That's known number. What is the location at the wall? That's R equal to capital R. That's at the wall. Vz is 0. So put 0 over here. That means the whole term moving to the right or to the left, that's C2. Okay? So now you get C2 equal to P0 subtracted by PL over 2 mu L times capital R squared over 2. That's C2. So plug C2 back here. You get Vz. You can see that the term pressure, 2 mu L, and these two are common. So you can take it out. So you get P0 PL over 4 mu L. Okay, it is common. And C2 is positive. The first term is negative. So I'm going to put C2 first. That would give you R squared subtracted by small r squared. Okay? To make it a little bit more clear, I am going to bring this capital R squared out. Bring it out. Inside, there's 1 left, subtracted by small r over capital R squared. That's your velocity profile. And you will realize that if you checked at r equal to 0, this term turns to be 0. The rest should be maximum velocity. Okay? So the first term will be defined as V maximum. At r equal to capital R, this ratio turns to be 1. This will be 0. Then Vc equal to 0 at the wall, according to what we defined earlier. So the equation seems to be correct. So whenever you end up with the equation, please check that it follows your boundary condition. Any question? Now, if you plot this velocity profile between Vz and R, you see that at r equal to 0, 0 is here, velocity turns to be maximum. That's Vc max, or V max. It is here. At r equal to capital R, velocity is 0, is here. In between, the function depends on r squared. So it is parabolic. So it looks like this. Okay? If you map this picture into the system, if you draw this system, this line. At r equal to 0, velocity is maximum. This is Vmax. At r equal to 0, it is 0. I'm sorry, at r equal to capital R, it is 0. In between, it is parabolic, and it is symmetry on both sides. So you have velocity profile looks like this. Just like what you learned in unit operation 1. In circular tube, for laminar flow, you have parabolic velocity profile with maximum velocity at the center. Okay? Also, before we dismiss the class, this equation, which is shear stress profile, if you plot between tau rz with respect to r, you get at r equal to 0, tau is 0. So it's 0 here. At r equal to capital R, tau is somewhere maximum, right? In between, it is linear because r is to the power 1. This is linear function. So it looks like this. If I map on the system, you have to understand that everything goes down. Okay? At r equal to 0, tau is 0. At r equal to capital R, tau is somewhat maximum. In between, it is linear. And this graph must be duplicated on the other side as well. Right? Because at r equal to capital R, it is this point as well as this point. So tau looks like this. Of course, it's flipping down. In this graph, it's going up. This is going down because your z-axis is going down. Okay? Last thing is, we are all aware that tau Rz is the momentum flux. It's a transfer of z momentum in r direction. It always goes from high velocity to low velocity. So high velocity is here, low velocity is there. So according to the velocity difference, you should expect that the direction of the transfer is going from the center outward, right? From the center here, going either side are considering that going outward. Whenever you go from outward direction, you go from maximum velocity to lower velocity. So momentum transfer, or z momentum, is transferring in plus r direction. Okay? And your momentum is going in plus z direction. So your flux is going in plus r, plus z, in direction of momentum itself, is going into plus r in the direction of the transfer. Plus and plus, making the whole vector, the whole tensor here, to have positive sign. So you can see that tensor here is always positive. All right? Next example, I will show you how this tensor should have negative sign later on. All right, we have maybe still 10 minutes left. Let me finish with this one. We will use this again later on, but if I want to calculate force of liquid acting on the fluid, force of liquid acting on the wall, that's associated with friction force. In unit operation 1, you learn about friction factor. Friction factor is about flow of the fluid on the wall, right? So if I want to know magnitude of the force that fluid is acting on the wall, this force is supposed to be equal to the force that the wall acts on the fluid. According to the Newton's third law, action equal to reaction. Okay? So we can calculate this force based on the force that liquid acts to the wall or wall acts to the liquid. Doesn't matter. Okay? This is the force that liquids act. Okay? At the wall, it would be equal to tau Rz at R equal to capital R. That's the shear stress at the wall, multiplied by the tau should have unit of Newton per square meter. In order to get Newton as a force, you need to divide by square meter, you need to multiply by square meter, which is the area. This area would be area that force acting on the wall. That would be inner circumference of the pipe multiplied by the length. So that would be 2 pi capital R times L. Okay? So shear stress profile was determined. At R equal to capital R, this tau would be pressure divided by 2L times capital R. Times 2 pi RL. That would give you modified pressure. 2 cancel out, L cancel out, you get pi R squared. Okay? This would be the magnitude of the force that wall acts on the fluid or fluid acts on the wall. The magnitude would be the same. So if you take the fluid from Z equal to 0 to Z equal to L as a whole, and you draw this system, this is liquid, okay? You see that force associated with this body includes mg, pressure from above, pressure from below, and force from the wall. Right? Question is, force that wall acts on the liquid, does it go up or go down? Think about this. Force that the liquid acts on the wall must follow direction of the flow. If the liquid flows down, force that liquid acts on the wall goes down. That means force that the wall acts on the liquid goes up. Okay? So we have Fk going up. Of course, Fk going on both sides, all the way. All right? So if you're trying to do the force balance, like what you did in mechanics, pressure going down, if you take a balance of pressure of force going down, that's P0 times cross-section area pi R squared. This is P0, this is PL. gravity force, mg, that's density times volume, pi r squared L g. That's mg. So these two terms are basically force going down. Force going up is basically pressure at L times pi r squared added by Fk. Right? If you solve for Fk, you see that you have pi r squared. If you move this to the left-hand side, pi r squared will be common term. Take pi r squared out. What you have left would be P0 subtracted by PL plus rho GL. And PL and rho GL can be combined as modified pressure, PL. P0 add rho G0, you get modified pressure P0. So this would end up with pi r squared, modified pressure P0, and modified pressure PL, exactly like what we did here. So whether you do it from microscopic balance, from shear balance, or macroscopic balance, you should get the same answer. Okay? All right, time is up. Any question? There will be. I will give it to you soon. I want to make sure that you can do this first before assigning homework. Otherwise, you can just you will just copy my homework.
How many homeworks do you think will be
On this semester, maybe 5, 6. Yeah, maybe 2 homeworks for each session. All right. So if there's no question, next week I am going to modify these examples to something a little bit more complicated and try to work on that. All right? So see you next week.